Hi. In this video, I'm going to give a quick review of Noether's theorem, and we're going to specifically think about it in a context of Lagrangian mechanics, so classical mechanics, working with Lagrangians. So again, what does this theorem teach us? It says that for each conserved quantity is associated with a symmetry in nature. So conservation laws are things that are incredibly useful in physics. You should think about all of the conservation principles you have as being another tool in your toolbox for solving problems. You see this right away in intro physics when you learn about conservation of energy and you learn that you can calculate everything that you were doing with kinematic equations and vectors using instead the conservation of energy. And hopefully you saw that it was a lot more convenient and a lot easier to calculate things using that conservation principle. And so Noether's theorem really gives us a deeper understanding for where these conservation principles are coming from, why these certain things are conserved and other things aren't conserved, and why for one particular system something might be conserved, but then why in this other system, why is that conservation principle, why doesn't it hold anymore? So to give some examples, so energy, right? This is one of the first conservation principles you probably learned about. Energy is conserved because of time translation invariance, which is to say our laws of nature are not changing in time. Our laws stay the same, and that is why energy is conserved in time. Momentum is associated with a spatial translation invariance. Angular momentum is associated with a rotational translation or rotation, right? So the fact that if you rotate your physical system, um, the laws that the equations of motion that it obeys aren't going to change, tells you that your system is going to have the conservation of angular momentum. And this list can go on, but these are sort of the most familiar examples. And so we want to see, well, we won't actually see how this works in an example, but how is this going to play out in our Lagrangian mechanics formulation of classical mechanics? So how can we understand Noether's theorem in this context? Well, we want to consider some sort of transformation. So we'll consider an infinitesimal transformation, which is to say a very small one. So we have our generalized coordinates Q, which again, Q is just this letter we use in Lagrangian mechanics to represent our different coordinates. And we use it often because usually we aren't just dealing with basic X, Y, and Z Cartesian coordinates. We might have R and theta as polar coordinates, or we might have something that's even more sort of strange. Um, and so we use Q as our normal letter. So we have some system, we have some set of coordinates Q that describe the configuration of our system as a function of time. And we're going to say, send our coordinates to some Q prime, which is some function of our original coordinates, and then epsilon, that should be an epsilon, which is some small parameter. Um, this is our new coordinates, and Q are our original coordinates. right? The prime here is not a derivative. This is just saying Q prime is some new set of coordinates to distinguish them from Q. The Q's are original coordinates. So what we're doing is we're considering some transformation, right? So we could be translating our coordinates. We could be rotating our coordinate system, right? Again, with these familiar examples, or you could do all sorts of things. This transformation is said to be a symmetry if the Lagrangian does not change when you make this transformation. So this is a symmetry if the derivative of the Lagrangian, so the change in the Lagrangian with respect to that small parameter epsilon, which parameterizes our change, if that derivative is set to 0, which is to say the Lagrangian doesn't change, then this is said to be a symmetry of our system. Now, if we use this fact and use the Euler-Lagrange equations and massage things a little bit, then one can derive a conservation law. And I'm not going to do this in this video, but you can work through it, and it's not actually that challenging. It's just sort of not what I want you to get out of this video. The conservation principle, which states that the sum over all of our coordinates, right? These are the coordinates of the partial derivative of our Lagrangian with respect to our generalized velocities. And here, these Q are our original coordinates. Right, so here, this first term, it's just you're just taking the derivative of the Lagrangian with respect to Q dot, just like when you use the Euler-Lagrange equations, right? And you do this for each of your coordinates, and then we're going to ultimately sum over that. And then we're going to multiply this by the derivative of our Q primes with respect to that small parameter. So we take that derivative of Q prime, our new coordinates, with respect to epsilon, and then after you take that derivative, you set epsilon equal to 0. And we could calculate this thing, and this whole thing is equal to a constant. Again, I didn't derive this formula for you. I'm just telling you that. And I'm telling you that all that it comes from, again, is we start with assuming you're given some transformation, which tells you Q prime, it's a new set of coordinates, Q prime, written as a function of our original coordinates plus some small parameter epsilon. I give you that transformation and you plug it into your Lagrangian and show that the Lagrangian does not change with respect to that small parameter epsilon. If you know that that's true, then we could calculate this thing on the left-hand side of this box, and that will be a constant in time, which is to say it's conserved, right? This is constant in time, or in other words, conserved. So you could look at examples where, for instance, you consider a spatial translation of your Lagrangian and then calculate this thing and show that, for instance, that might be conservation of momentum. So you'll find on the right-hand side, this is your momentum, and you find that momentum is conserved. These will not always be associated with really familiar things like momentum, right? If you consider some weird transformation that your Lagrangian happens to be a symmetry of, it might be associated with some weird quantity that we don't have this good classical physical intuition for, and that's okay. Because maybe the symmetry you considered is somehow associated with the sum of momentum and angular momentum. I don't know, that's a weird thing to consider, right? But you could, or somehow it's proportional to something like that. And then you think that that's some weird thing you've discovered, but it's just you showed that momentum plus angular momentum are conserved. Okay, those are different units. So But hopefully it's clear. The thing that you find is conserved might not be a normal familiar classical thing, but these are still going to be very useful. So conservation principles are always going to be useful things, and this is how, given some transformation that your Lagrangian is invariant under, this is how you can calculate what that conserved quantity might be.